Hello, everybody. My name is Masood Olia, and I'm a faculty at the School of Engineering here at Wentworth University. And I'm here with a very simple problem or concept of how we can figure out velocity or acceleration of a point on a rigid body, which is in pure rotation. Okay, as always, guys, I would appreciate after you watch the video, if you could like the video and even subscribe if you want to see more videos of this type. Okay, so what we have here is basically, let's say if you have a rigid body, right? And this rigid body is rotating about some point. Actually, it's an axis which passes through this point. So that point, the pivot point, is the center of rotation. Let's say this guy is rotating with some angular speed, omega. Remember, omega is called angular speed or angular velocity. If you think of it as a vector, we call it angular velocity. In two-dimensional, the rotation is either clockwise or counterclockwise. In this case, it's rotating clockwise. In fact, if you wanted to describe this guy as a vector, it would be whatever the magnitude of omega is. Since clockwise rotation is negative z-axis based on if this is positive x, positive y, positive z is coming out of this, page, right? So this would be actually a negative omega k. But actually, I don't want to use the, the vector approach. I want to use what I call the scalar approach. So let's say now at this instant, you want to find, say, velocity of a point, say this point here. I wanted to change this to red. It didn't take it, but that's all right. So let's say this is point A. Okay, some point. It doesn't have to be on the outside of the body. It could be anywhere on the body. All right. So the way this is done actually is very simple, the scalar approach. You connect from the center, the pivot point, to this point, and that establishes your radius. Basically, the definition of rotation is that this point will go along a circular path like this with a radius that is established here. So velocity of this point, therefore, is equal to, let's go back to, is simply r times omega. So the magnitude of velocity is r times omega. And this velocity is always tangent to the path of motion. In this case, that means it's actually 90 degrees to the radius. So that would be the direction of the velocity. Or let's say if there was a point here, you establish r. This time r is a little bit larger. And then the velocity would be what? Like that. All right. So this is velocity of A, for example. If this is point B, this would be velocity of point B. And the velocity of point B would be this new radius times omega. And why did I show them down and up like this? Because they follow the direction of omega. So since the body is rotating like that, velocity of A would be down and velocity of B would be up and to the left. So very simple concept. So actually, let me do a quick example of this, really trivial. And now I want to show you a simulation to just verify it for you. I'm using a software called Working Model 2D, which is a very simple software, but very powerful. All right, so let's say if you have a plate in the shape of a triangle, right? Where this is 4 meters, right? And this is 3 meters, right? And let's say I put a motor here, and this becomes my center of rotation. And say this motor will rotate this guy with an omega of, say, 10 radians per second counterclockwise, right? So basically, this is your rigid body, like a shape of a triangle. So I'm going to actually look at 2 points, point A right here and point B here. I'm going to say, okay, what would be velocity of A and velocity of B? Remember, this is a constant angular speed, so the angular speed doesn't change. So for A, let's establish our R. So what is R? R is from the pivot point to point A. So this is a 3, 4. The hypotenuse would be 5 for A. So velocity of A, therefore, would be r times omega. R is 5 meters. Let me actually carry out the unit. And the unit of omega, which is 10, magnitude is 10, and the unit is radians per second. Look what happens here. 5 times 10 becomes 50. And meters radians per second. Remember, radians is dimensionless, so you don't have to really put it there. So that would be 50 meters per second. What about the direction? Direction would be like this, 90 degrees or perpendicular to the radius at that instant. And then that, of course, this is going to rotate, but that velocity would be always 90 degrees to that radius. And similarly, velocity of B should be like that, up 90 degrees to what? To this radius, this one. Of course, this is a radius of 4 meters, so velocity of B is going to be what? It's going to be r times omega also, but r is 4 meters times omega of 10 radians per second. So as you can see, this is a very trivial problem that I'm showing you. That would be 40 meters per second. So that was velocity of A like that. This is velocity of B like that. Okay, so you see how easy it is to do the velocity. Now, if you wanted to do it vectorially, that's a different story. Velocity as a vector is the cross product of omega as a vector and r as a vector. Okay. Or again, it's the same r. It's from the pivot point to the point, but you have to represent that as a vector in order to find the velocity. Now, of course, when you have a velocity as a vector, you do have the magnitude and the direction. Here, I just show you the scalar approach, which means you get the magnitude and you get the direction based on the fact that velocity vector has to be perpendicular to the the radius. All right, I have this software working model here, and I can show it to you by, let me actually, so I've already generated these 2 points. This is, as you can see, this is 4 meters and this is 3 meters. These grids are 3 meters, 1 meter each. And I can even bring a, establish what we call show me the vector, velocity vector, and the same thing here. For point B. So we can see actually the vectors. So I'm gonna, and by the way, I have to, if I bring the motor property, you see this is operating based on velocity, angular velocity of 10 radians per second, and it's going counterclockwise right now. Okay, so look, if I run it slowly, look what happens. Ooh. We actually just go around. These velocity vectors are relatively large. So let me kind of zoom. There we go. Look, I made it small. And look, velocity of A and velocity of B are exactly what they're supposed to be. And they are not going to be changing. The direction, of course, is changing, you see. But you see, velocity of B is always 90 degrees to that hypotenuse. See that here? That velocity is 90 degrees to the hypotenuse. And velocity of B is always what? 90 degrees to that 40 and 50 meters per second. I think I'm going to stop here, guys, and show you in another video how you can, handle acceleration of a point in a rigid body in pure rotation. Again, thank you for watching and listening, and I'll be back soon. Okay.